In this video, we will go over the basics of limit. We will see what the limit of a function is, we'll write down some limit laws, and we will see different functions that behave differently around a limit point. So we are discussing here limit of a function and limit laws. Roughly speaking, what we are interested in this section is we are interested in how a function behaves near a particular value. Near a particular value, let's say x equals to c. The emphasis here is that we stay near a particular value. But not at x equals to c itself. We're going to work around the value x equals to c. And then see, as we move around the value x equals to c, what is the response on the y value? How does that behave? As we go close to c, what is happening on the y-axis? For example, take this function. I take this function. Let's suppose the graph of the function is something like that. And we are interested in checking the limit at this particular value. Let's call it x equals to c. Now, because this is the graph of the function y equals to f of x, then this value over here, let's call it L, would be equal to f evaluated at c. Now suppose that I am standing at this point on the x-axis right now, right here, close to c. Then my y value on the y-axis would be over here. I go further close to x equals to c. I go here. That means my y value on the y-axis is getting closer to the orange dot. If I go further close to x equals to c, as close as possible, you can see that my blue dots are getting as close as possible to the orange dot on the y-axis. But there is a direction. As I move towards x equals to c this way, my y values are moving towards L this way. Let's check on the other side. Suppose I'm here, a bit further away from x equals to c. My y value is this pink dot here. Let's go closer. My y value is this pink dot here. Now again, I go close to c, as close as possible. My value on the y-axis would be closer to the orange dot, as close as possible. So as I go close to x equals to c this way, the same thing is happening. My y values are getting closer to this orange dot, which we are saying has a value L on the y-axis. So in this case, when we move towards x equals to c from both sides, our value on the y-axis is going towards the value L. If that happens, we say that the function has a limit L as x approaches c. And you can see that here. There was no point when we talked about what is happening exactly at x equals to c. We are not interested in that. And you will see later on the value of the function at the point x equals to c might be different from the limit of the function as x approaches c. So let's write the formal definition of the limit, and then I'll show you some examples. If, defining the limit and introducing the notation, if f of x is arbitrarily close to the number, let's say L, as close to L as we like, as we can imagine, for all x, that are sufficiently close to x equals to c, and I'll emphasize again, other than c itself. Then we say that f approaches the value L, or f approaches the limit L, as our x approaches c. And we write in notation, and write limit x approaches to c of f of x equals L. Remember, we do not mean, you will see that in the coming example, I do not mean to say that here f of c equals L. It might happen in some cases that the limit is the same as the value of the function at the point, but this is not what we mean here. Not what we mean. What we mean here is that as you go close to the value x equals to c, the value of the function on the y-axis would go close to the value L. Consider this example. And we'll do a contrast. I will consider a function f of x that equals x squared minus 1 divided by x minus 1. And I will consider another function, let's call it g of x, that equals x plus 1. Now, in my first function, you can see that I cannot take x equals to 1 because I have a 0 in the denominator then, and I have a 0 in the numerator then. I must write x is not equal to 1 in my original function f of x. But for g of x is any real number. No restriction on that. However, in the first one, I rewrite x squared minus 1 divided by x minus 1. Numerator is a difference of squares. It's x minus 1 times x plus 1 divided by x minus 1. I cross these two factors. I am left with f of x equals x plus 1. But remember, I am carrying this condition with me that x is not equal to 1. But that's not the case for the function in blue. Now what I'm going to do is, I'm going to plot these two functions. Let me make a grid. My x-axis, and there we are. Let's give it some scaling. This is my 1, This is my 2. That's my 3. And approximately here, -1, -2, and so on. On the y-axis, I go by 1 here and 2 here. And this would be -1. This is the function that I'm trying to plot. It's a linear function. The graph is going to be a straight line. You can see that when x equals to 0, y equals to 1. That means it's this point here. When x equals to, for example, -2, my y value is -1. Or if you put your y value equals to 0, you're going to have x equals to -1. You got 2 points. We can join these 2 points together, and we can extend both ways indefinitely because it's an infinite line. However, you see, I cannot substitute x equals to 1. So at x equals to 1 and y equals to 2, there is an empty circle on the graph. Going over here and then moving away like that. So there is an empty circle. I cannot say the value of the function at x equals to 1 is 2 because I cannot even use x equals to 1. The original function is not well defined at x equals to 1. It's not a problem with the second one though. The one in blue will have a graph of a straight line with no gap on it. It'll be something like that. Okay. Now, let's check the limit of the function when x goes to 1. I do not have the value of the function at x equals to 1 again. Function is not even defined at 1. I cannot even talk about this value. Suppose I walk towards x equals to 1 from that side. I take, for example, x equals to 1.2. F of 1.2 would be equal to, I'm using this function, 1.2 plus 1. This is 2.2. That value, if 1.2 is here on the x-axis, then 2.2 would be somewhere here on the y-axis. I'm going to go close to 1. 1.1. 1.1 plus 1 equals 2.1. If I have moved over here on the x-axis, my y value has moved over here on the y-axis. So if I'm going this way on the x-axis, I'm coming this way. If I'm coming this way on the x-axis, I'm coming down this way on the y-axis. I can go close to 1, as close as possible. I can try to compute what is f of 1.001 plus 1. This would be 2.001, but I cannot go exactly at 1. Now come on this side. Suppose I take 0.8. I'm on the other side, but I'm still close to 1. F of 0.8 would be equal to 0.8 plus 1. This is 1.8. I would be somewhere over here on the y-axis. Let's go closer. 0.9. F of 0.9 would be 0.9 plus 1. It would be 1.9. I am moving close to 2 over here as well. I go really close to 1 now. 0.999. 0.999 plus 1. This is 1.999. As I go close to 1 from this side, I am getting closer to 2 from this side. So it seems to me that from either side, when I go close to 1, my value on the y-axis is going closer and closer to y equals to 2. So therefore I can write for this function limit as my x approaches 1 of this function f of x, the limit of this function would be equal to 2. And once again, we do not mean here that f of 1 equals to 2. We don't mean this. What we are saying is, as you go close to x equals to 1 on the x-axis, you'll be going closer to 2 on the y-axis as a y value. Okay, now consider this function. I'm going to modify this function. I'm going to create a piecewise function. Suppose I have, consider f of x, or maybe let's create a new one. Let's call it h of x. That equals, it's a piecewise function, x squared minus 1 divided by x minus 1, only when x is not equal to 1. And it's equal to, let's say, 1 over 2 when my x equals 1. Let's try to graph this function. I'm going to deal with the case when x is not equal to 1 first. I will avoid this value x equals to 1. Let's move it over a little bit. 2, 3, negative 1, negative 2, negative 3. I'm taking this as 1, this as 2, and so on. So the graph would look like, again, x squared minus 1 divided by x minus 1 would be x minus 1 divided by x plus 1 divided by x minus 1. This is equal to x plus 1. And for this branch of the function, x is not equal to 1. When I graph it, the graph of y equals to x plus 1 is again this straight line. But since x is not equal to 1, I will have to move my y value up a little bit. At this point, I have an empty circle. It keeps going. There is a gap, same graph, and it then moves on. This value is 2 on the y-axis, this is 1. Now when you come to this part, it says the value of the function at x equals to 1 is 1/2. So this is the value of the function right here. If this is 1 by 2. Now it's the same function. I'm not stepping exactly at x equals to 1, so I'm not looking at the value of 1 over 2. When I do this limit, still limit x approaches to 1 of this function, now h of x, still equals 2. If you stay close to 1, for example here, you will be going closer to 2 on the y-axis. It's the same function. And same is the case on this side. If you go closer to 1 from this side, you're going closer to 2 on that side. If you go closer to 1 on this side, you're getting closer to 2 on this side. If you keep squeezing this band from either direction, you're also squeezing this band with 2 in the middle. But now you can see that h of 1 is equal to 1 over 2. The value of the function at x equals to 1 is completely different from the value of the function, or the limit of the function, as x approaches 1. And that's the point that we were trying to make. Let's write that down. Limit of f of x may be completely different from the value of the function at x equals to c. Just like in this case. Now, for example, if I define another function here, let's take p of x. Because I have the freedom to choose the value at 1, I'm defining a new function, x squared minus 1 divided by x minus 1 when x is not equal to 1. And I define the function to be equal to 2 when x equals 1. Now in this case, limit x approaches to 1, p of x equals to 2, but p of 1 also happens to be 2. The limit of the function is exactly the same as the value of the function. But it's not necessarily true. Not in all the cases. All right. Sometimes a limit may also fail to exist. A limit may also fail to exist. Let's consider a few examples where such a thing happens. First example can be, I define a piecewise function. It's a well-known one. F of x equals -1 if my x is less than or equal to 0, and it's equal to +1 if my x is bigger than 0. What is the graph of this function? If these are our coordinate axes, if x is less than or equal to 0, the value of the function is -1. That means it has a constant value of -1, including at 0. I'm going to put a dark circle here, when my x is less than 0. But when my x goes bigger than 0, when my x is positive, the function jumps to +1. It goes to a value +1 and then stays there. It's a constant value. The function doesn't change that value. Now you see that if you are going close to 0 from this side, the value of the function is 1 all the time. For example, here, the value of the function is 1. At any point on the right of 0, the value of the function is +1. But if you come on the other side, if you're going towards 0 from this side, the value of the function drops down to -1. Same is the case over here, at any point on the left of the origin. So in this case, I would say that limit x approaches to 0 of this function f of x does not exist because it changes value. If you're coming towards 0 from the right side, the value is different from the value when you go towards 0 from the left side. If that happens, we say the limit doesn't exist. It doesn't have the same value from both directions. But it has a well-defined limit at any other point. For example, if this is x equals to 3, if you are close to 3 right here, your value is +1. If you are close to 3 on this side, your value is still +1. it's only at x equals to 0 that the limit doesn't exist. You can write that the limit x approaches to 3 of this f of x equals plus 1. And if you take any negative value, limit x approaches to, for example, negative 2 of f of x, that would be equal to negative 1. If this is negative 2, from both sides, you're always at the value negative 1. We don't have any problem around negative 2. The function jumps as you move around the value, x equals to 0, so the limit does not exist there. Another example. F of x, again a piecewise function, is given by 1 over x, and x is not equal to 0. And it's 0 if x equals to 0. So for this part, because I have x in the denominator, I'm taking out the value x equals to 0 so that I don't have a problem there. And then I redefine the value of the function at 0. I'm saying the value of the function is 0 when x equals to 0. If I plot this guy, for the first branch, when x is not equal to 0, if you remember the graph of 1 over x, this branch over here, and I have this branch over here. But there is one more thing that is involved here. The value of the function at 0 is given as 0. So this origin is also part of the graph because of this part. Now you can see that there is a vertical asymptote at x equals to 0. For this part I'm talking about. If I approach x equals to 0 from this side, my function is shooting up towards infinity. For example, if you take x equals to 0.1, f of 0.1 would be equal to 1 over 0.1, that's equal to 10. If I go further close to 0, f of 0.01, which is 1 over 0.01, that's equal to 100. So as I keep getting closer and closer to 0, my function keeps getting bigger and bigger and bigger values. And it's not going to settle down to any fixed value. If your x keeps getting smaller, your y keeps getting bigger. It just goes to infinity. And if you go towards 0 from this side, the only difference is that the function is sliding towards negative infinity. At negative 0.1, you will get negative 10. At negative 0.01, you would get negative 100. So the limit doesn't exist. But the limit is also undefined here. Limit x approaches to 0 of this function f of x is undefined. It's not settling down to any finite value from either side. It goes to either plus infinity or negative infinity, depending on the side that we are approaching the x value from, x equals to 0 from. But once again, if you change your x value, for example, if you choose this, x equals to 1, then it's okay. You can say that the limit x approaches to 1 of f of x, it exists and its value is equal to 1. It's only the 0 where we have a problem. Alright, in this case the function is unbounded. In the previous case it was jumping between two values, negative 1 and plus 1. Here's another example. G of x equals, let's say, 0 when x is less than or equal to 0, and its sine 1 over x if our x is bigger than 0. Right, let's graph it again. Let's see what's happening here. The function has a 0 value for any x less than 0, including 0. This orange part is part of the graph, and it keeps going towards the left side. Sine 1 over x, that's a highly oscillatory function here. I'm putting dots because it oscillates too fast. Sorry. I lost it. There. It's oscillating too fast here. But it'll still be after that the graph of the sine function. And so on. It'll be ongoing. So I can say for this function, it's too fast in its oscillations. To have a limit. To have a limit at x equals to 0. You can see the value where we have a problem is x equals to 0. Okay. And this function that we wrote at the start, let's mention that over here again, f of x equals x squared minus 1 divided by x minus 1 when x was not equal to 1, and 2 when x was equal to 1, or maybe 1 over 2, doesn't matter. The limit existed at x equals to 1, and it has a value of 2. Limit x approaches to 1, f of x was equal to 2. And doesn't matter what value we choose at x equals to 1, the limit still equals 2. This function, where the value goes from -1 to +1 at x equals to 0, the function doesn't have a limit. Same is the case with this function, and same is the case with this very fast oscillating function. Does not have a limit at x equals to 0. So a function may have a limit, but a function may not have a limit either. All right. Now, let's write some properties and some limit laws. First, if you take the limit x approaches to c of the function f of x, which equals x, this would be equal to just c. The function equals x, y equals to x, straight line. Doesn't matter what c you pick, your answer is always c for this function. If you have a constant function, suppose I'm trying to find limit x approaching to some value c, f of x, which is a constant function, f of x, let's suppose, equals k for all values of c. It's a constant function. In this case, the limit value would be irrelevant. My value would always be equal to k. For example, if you take f of x equals to 10, the limit of this function at every value of x is equal to 10, no matter what x we pick. Its limit is 10. It's a constant function, doesn't change its value. Then let's write some limit laws. And it's a theorem. So we are stating some results. If L, M, C, and K are real numbers, and I'm going to assume that limit x approaches to c of the function f of x equals L. I have a function f. When x approaches to c, it has a limit and it's equal to L. And further, limit x approaches to c of a function g of x, suppose that equals to the number m. Then we have the following properties. First, limit x approaches to c of f of x plus and minus g of x. I'm adding two functions together or subtracting, and I'm taking the limit. This equals limit x approaches to c f of x plus or minus limit x approaches to c of g of x. Or in other words, we can say that limit of the sum of the two functions or difference equals sum or difference of the limits, both the functions. Similarly, if you have limit x approaches to c of a constant multiplied by f of x, you can factor the constant out of the limit and then take the limit of the function first and then multiply the limit value with c. This would be equal to c. We are supposing that the limit of f is L. This would be c times L. And in the first case, because we are supposing these values for f and g when x goes to c, this would be equal to L plus or minus m. So if you have a constant multiple, the constant comes out, and if you have a sum or difference of two functions, you can actually take the limit separately and then add or subtract our result. Limit x approaches to c of f of x multiplied with g of x. You have two functions multiplied together and you're taking the limit of the product. You can actually take the limit of the functions first and then multiply them together afterwards. G of x, that equals L multiplied by m. So I can say limit of the product is product of the limits. Similarly, limit of the quotient f of x divided by g of x, this equals limit x approaches to c of f of x divided by limit x approaches to c of g of x, provided the limit of g as x approaches to c is not equal to 0, because otherwise we would be dividing by 0. This would be equal to L divided by m. Let's emphasize that here, provided m is not equal to 0. That's for the quotient. Then for the power, limit x approaches to c f of x raised to the power n. Okay, we are taking the limit, but f is under a power n. Again, you can take the limit inside f of x and then raise to the power afterwards, L to the power n. N would be a positive integer. N is a positive integer. Similarly, if you have radicals, limit x approaches to c f of x raised to, let's say, 1 over n. Still, you can do limit x approaches to c of the function f of x all raised to power 1 over n, this would be equal to L to the power 1 over n. And again, you would say n is a positive integer and not equal to 0. It's a positive integer. Let's do an example now and see how we can apply these rules. Compute limit x approaches to c of x cubed 4x under the root negative 10. Now you can think of that as a sum of 3 different functions. This is my first function, this is my second function, this is my third function. At this stage, because we are still learning the limits, I'm going to apply this first rule and write the limits separately, individually. Limit x approaches to c of x cubed plus limit x approaches to c for root x negative limit x approaches to c of 10. Now, for the first one, x cubed, when we are taking the limit of that, our very first term, it corresponds directly to property 5. My f of x is x and n is 3. So using that property, I can write limit x approaches to c of the function x, and then later on, I can take the power 3. Plus, first, I am applying this property, scalar multiple. I have a constant multiplied with my function. As a first step, I write 4, limit x approaches to c, root x under the root. A constant multiple, which is 4 here, can be pulled out of the limit. Negative. Now I apply this property that we wrote over here, that limit of a constant function is the same function value. So in this case, I know limit as x approaches to c of 10 would be equal to 10 because it's a constant. For the first one, limit x approaches to c of x, that's again the property that we wrote here at the top. This is equal to c. And then I have 3 on the top. Using property 6, I can write 4, limit x approaches to c of x, all under the square root, which is 1 over 2, negative 10. I put the limit inside. This is c. I am left with c cubed plus 4, c under the root, negative 10. And now, of course, when we have enough practice, then we can do it faster. For example, if I follow it up with another example of a similar function, limit x approaches to 1 of x squared plus 2x negative 5. Now I know in this case, this is going to be 1 squared. Limit of x when x approaches to 1 is 1. I have a square outside. 2, limit of x again is equal to 1. When x is going to 1, 2 is a constant multiple that can be pulled out. I'll get 1, negative 5 is a constant. That stays as it is. This equals 1 plus 2, negative 5. Our limit value is equal to negative 2. So now we can do a little bit faster because we know the limit laws and we know how they apply over here. One last result that I want to mention here is, again, let's write that as a theorem. And it's about limits of polynomials. if f of x equals a polynomial, an x to the n plus an minus 1 x to the n minus 1 up to a2 x2 a1x plus a naught, an minus 1, a2, a1, a naught, they're all constant values, constant numbers, real numbers. And you never get a negative exponent on x. And no radicals, all integer, positive integers. In that case, limit x approaches to c of f of x is simply f of c for polynomials. Now that's really handy. For example, if I'm doing the limit x approaches to 2 of x cubed plus 2x squared negative 3x negative 1, because this function in the bracket is a polynomial, this is simply 2 to the power 3, 2 to the 2, 3 times 2, negative 1. This is 8 plus 8, negative 6, negative 1. This is 16 minus 7. Minus 7. We get a value of 9. So if it's a polynomial, you can simply just replace every x by c. And x is the value that we have the limit on, x approaching to c.